All right. It's about time to get started, so let us begin. We've got an exciting section to finish off today. Remember, we were solving trig equations. So last time, we said, okay, there's infinitely many solutions to these equations. And we are going to find them all, but most of the time, we're going to do like what we did in example 2, and just solve the equations for theta in 0 to 2 pi. Okay. And then remember, to solve the trig functions, we say to solve the trig equations, first we try to get it to look like this, where we solve for the trig function. So, you know, we added 3 and then divided by 2. We added 1 divided by 2, took the square root for this one. All right. And then we solve it like we did example 1. So that's all we're doing today. We're just going to do it a little trickier, all right? Sometimes we'll have to approximate. I love exact answers whenever you can. But sometimes we have to approximate. And that's what we're going to cover today. And this is where things get pretty dicey. But don't worry. I think 9.3 and 9.5 are some of the hardest sections of the entire class. So after today, I don't want to say we're going to be on easy street. But after today, it gets a little bit better. So just stick with me. We got example 3 here. Approximate all solutions, so not just 0 to 2 pi, all solutions to 4 decimal places. All right, and we've been using radians this whole section, so I'm going to keep using radians, but usually I don't have too much of a preference unless I ask. So part A, sine of theta equals 0.8. And now you might say, oh, 0.8. 0.8 is 4 over 5. We could draw a triangle. And yeah, you could draw a triangle. But there's still no angle. A 3, 4, 5 triangle has really nice sides, but it doesn't have really nice angles. We can't find the exact angle, or at least, I'm sure it's, I don't know, I'm sure it's possible some way, but not with techniques that we know of in this class. So we're going to have to approximate it. So we just do what we did before. You don't need to know that 0.8 is 4/5. No, you don't need to know that. Although if you're curious how you would know that, 0.8, right? This is literally 8/10. Or even more simply, it's 0.8 divided by 1. Either way, it's 8/10, which does reduce to 4/5, but yeah, you don't need that. You don't need that. So we need to solve this. No law of cosine, not yet. That's 10.2. All right. So we need to find our reference angle and find the quadrants. So this is the exact same method we used on Wednesday, way back when. Way back Wednesday. So we need to find the reference angle and the quadrant. The only difference is we cannot find the reference angle with our special triangles. We need to approximate, okay? So we need to look at, okay, if sine of theta is 0.8, one of our thetas will be the inverse sine of 0.8. Again, we're using radians here. So make sure you always know whether you're using radians or degrees. So you type in inverse sine of 0.8. And you get that it's approximately equal to 0.9273 radians. All right, if we were using degrees, we would say degrees. Since we're using radians, we don't have to say anything. All right. Excuse me, today. So this is one of our angles. That's our reference angle. And let's just get an idea of what this looks like, okay? Let's convert it to degrees, just so we have an idea of what it is. Because unless you are a radian fanatic, you probably don't know what 0.9273 radians looks like, okay? So if we convert it to degrees, remember you can convert radians to degrees by multiplying by 1. So we multiply by 180 divided by pi. And that's going to be about 53 degrees. So we can get an idea of what this looks like. 166 degrees, not the worst guess, but not quite it. All right. So that's our reference angle. 0.9273. But remember, 53 degrees is a little bit more than 45. That's only our answer in the first quadrant. My head is blocking this. There's also an answer in the second quadrant with the same reference angle, right? These are the same reference angles. So to find this thing in the second quadrant, we need to go 180 degrees or pi radians and subtract the reference angle to go back. All right? Because we know we're in the first and second quadrants because these are the two quadrants in which sine is positive. Remember ASTC? Everything, all things are positive here. Sine's positive here. Tangent's positive here. Cosine's positive there. All right. So we found the reference angle. We know the quadrants. We can find all the answers now. So theta is going to be our answer in the first quadrant, 0.9273. And then again, we're asked for all solutions here, not just 0 to 2 pi. So we also have plus 2 pi k. And then we need the answer in the second quadrant, which remember is going pi radians minus our reference angle. So pi minus the reference angle, which was 0.9273. And what is that approximately equal to? Pi minus 0.9273 is approximately equal to 2.2143. And again, you can't see that. You can only see my shoulder. But that'll be our second answer. 2.2143 plus 2 pi k. And that's how we solve these ones. So it's essentially the same process as we did last time with example 1. The difference is that now our reference angle needs to be approximated. Okay? And that's how you do these problems. So real quickly, I want to go through a part B. It's going to be exactly the same, but not exactly the same. So it's going to be, I guess you could say, different. If there's any questions so far, go ahead and ask them. Otherwise, we're going to do a similar problem, but definitely not exactly the same. Let's look at part B. Say we have secant of theta equals -4. And you might say, okay, we take the inverse secant of both sides. And that's not wrong. But you're going to run some problems if you try to type inverse secant into your calculator. There's no button for that. So the 2 pi k, what that is says it's all the coterminal angles, right? This is 53 degrees, but we could also go around another 360 to become 413 degrees or whatever, and go another 360 and another 360, and they're all the same. They're all coterminal angles, and they're all answers to this. But yeah, essentially it has to do with adding circles, adding another whole rotation around. All right. So what I would suggest for this one, Brock, is just don't even worry about inverses at all. Just convert this, get rid of the reciprocal function. Okay, because there's so many easy mistakes to make when you're doing inverse functions here. So just write this as 1 over cosine of theta equals -4, and let's just solve this for cosine of theta, and then we don't have to worry about reciprocal functions at all. And that's what I would recommend every single time you have reciprocal functions in this section. Just get rid of them. Reciprocal functions and inverse functions do not mesh very well. It just usually causes problems, and there's a lot of easy mistakes to make. And again, we can take the reciprocal of both sides, and that's still equal. So we get that cosine of theta equals the reciprocal of -4, which is -1/4. Okay. And now this just becomes exactly like we had it before. We need to find our reference angle. We need to find what quadrants cosine's positive in. Cosine's positive in the everything's positive in the first quadrant, right? So cosine's positive in the first quadrant. That's like first and fourth together. It's like I was combining the answer into one word. Yeah, first quadrant and fourth quadrant. Yeah, so that's where we're going to have our answers. And again, to find the reference angle, we just need to say, okay, what is the inverse cosine of negative a quarter? And this is where, I don't remember this problem. This one's kind of tricky. Wait, it's negative. We want it to be negative. First be darned. All right, it's positive in the first and fourth quadrants, but we want to know when it's negative. That's the second and third quadrants. Okay, I was wondering, I was like, this problem is going down a very strange path that I don't remember. And that was why. Because I wrote down the wrong Roman numerals. Okay, so what is the inverse cosine of negative 1/4? So you find arc cosine of negative a quarter. You're going to get that's about 1.8235 radians. And again, it's a good idea. It's a very good idea when you're doing these problems. Just get an idea of what this looks like in degrees. And if you just want to work the whole thing in degrees, go for it. But remember, if you do the whole thing in degrees, you're not adding 2 pi k. You're adding 360 degrees times k if you're using degrees. Right? 2 pi is just because 2 pi is all the way around the circle. If you're using degrees, it's going to be 360 degrees. So we want to find the quadrants that satisfy the sine of our angle. That's exactly it. Yes. These two quadrants because of the negative and the cosine. It's a good way of stating it. So we convert this to degrees. We get about, oh, this is interesting. We get about 104 degrees. So this is not our reference angle, right? 104 degrees, that's a little over 90 degrees. That's this right here is 104 degrees. The reference angle is the thing that goes right here. This is what we need to find. We need to find this angle. Okay, so again, just like before, how do we find this angle? We go pi or 180 over and then subtract. Wait a minute. That's backwards. That's if we're finding the other angle. What we do is we know this part and we know it needs to add up to 180. It needs to add up to pi. So 1.8235 plus our angle, our reference angle, needs to equal pi radians. So we just subtract 1.8235 from both sides. All right, and this is the confusing thing that can happen with cosine. Because sometimes cosine is going to give you an angle in the second quadrant when you use the inverse sign. Okay, so this cosine situation is a little trickier. So we just subtract this over. So one of our reference angles is going to be, again, let's just solve for theta, going to be pi minus 1.8235, which again, we just type into a calculator. Pi minus 1.8235 is going to be 1. We found our reference angle. It's going to be 1.3181. So that's the reference angle. Okay. So we have our reference angle. Now we need to find the angle in the second quadrant, which we already found. It was the 1.8235, and the angle and the angle in the third quadrant. Again, second quadrant, we found that up here. Third quadrant, we still need to find. And I'm running out of room here. So again, the two angles that we're looking for are this angle, which we already found. This right here is the 1.8235. We also need to find that same angle in the third quadrant, which is going to be what happens if we go pi radians and then an extra reference angle. We go pi radians or 180 degrees and then add whatever that reference angle is, which we already found. So the second one's going to be pi plus the reference angle, which is 1.3181. Okay. So what does that give us? That gives us about 4.4597. So we found the angle in the second quadrant. We found the angle in the third quadrant. Now we just need to add the plus 2 pi k. No, the reason why we're adding this angle instead of this angle right here is because this is our answer in the second quadrant. This is that whole 104 degrees. What we want to add is the reference angle. We want to go around pi plus the reference angle, and that's why we found out that the reference angle is this. Okay, because this 1.8235 is not that helpful. There are multiple ways of doing it, but it's not that helpful for finding this third quadrant angle that we need. One of the most straightforward, if I'm trying to be consistent in how I'm doing these problems, is to find this angle is to use reference angles. Because again, we know this reference angle down here. This reference angle down here is the 1.3181. That's why we're adding it to pi. Good question. So this is our third quadrant answer. This is our second quadrant answer. So we just combine both and add the 2 pi k's. So theta is going to equal to or approximately equal technically, right? 1.8235 plus 2 pi k and 4.4597 plus 2 pi k. Those are our two answers. No, there will be no Argand diagrams or functions of multiple variables in this trig class. So would you do 3 pi over 2 minus? So 3 pi over 2, right, is this. You wouldn't be subtracting the 1.823. Another way of doing it, though, Alex, if you wanted to do it, is you could also say this angle down here is negative this angle up here, right? This positive angle is the same as this negative angle. So you could have also just used negative 1.8235, which is this right here, and then added 2 pi to that to find the positive coterminal angle in this third quadrant. So that would have been an okay way of doing it as well. Using 3 pi over 2, though, right here, you could also subtract something, subtract this angle to get it, but we don't know this angle right here. It's not 1.823. Good questions. All right, we're going to move on unless there are more questions. That was example 3, last example of the day, but there's quite a few parts. This one is the real fun one, okay? This one is a juicy one, but I'm gonna flip the order of these. We're not gonna start with the worst one. We're gonna start with the better one. These problems are the ones that you're gonna hope I don't put on the quiz. Your quiz on Wednesday will just be over this section, all right? So, solve exactly where possible. So, approximate if necessary. Solve exactly, but approximate if necessary in the interval 0 to 2 pi. Yeah, Alex, rewatching the video is a good idea. Also, just start working on the homework today or tomorrow. And if you just get stuck in a problem or don't know what to do, send me a message on Discord or email me, okay? It doesn't have to be during office hours. If I'm free, I'll respond, okay? So don't hesitate about reaching out. All right, so example 4. Let's do part A. 2 sine squared of theta minus 5 sine of theta plus 3 equals 0. So I hope you've all been missing algebra, because this whole chapter has tons of algebra. And we're going back to algebra again, because what kind of an equation is this, right? Sure, it's a trigonometric equation, but we've got a sine squared of theta and a sine of theta. This is a quadratic trigonometric equation, yeah. So when you have quadratic terms like this, you solve it the same way you solve a quadratic equation. So yeah, one good way to do this is to use a substitution to look at this as a normal equation. Ax squared plus bx plus c, exactly, yeah. Or if you say, I don't like substitutions and you just want to factor it or use the quadratic formula immediately, go ahead. But go over off to the side, right? If we just say x is the sine of theta or something, then what does this become? Well, it becomes 2 times, well, the sine squared of theta just becomes x squared then. Minus 5 times, again, the sine of theta is x, plus 3 equals 0. And we can solve this. All right, the danger of using the substitution method is that you always have to remember to substitute back. If you substitute at the start, you got to unsubstitute at the end. So be careful about that. So there's a couple ways of solving quadratics, right? We could factor. We could use the quadratic formula. We could complete the square. And those are all the methods that'll work here. Don't get too excited about the quadratic formula. We're going to do that. We're going to do that in part B. Here we're just going to factor. So what we're going to do is I'm going to use the AC method. There's a couple ways of factoring this, but we just take the A times the C. We need to find what multiplies to 6, 2 times 3. That adds to the middle coefficient, -5. So the answer is going to be -2 and -3. And so we split up that middle term to get 2x squared minus 2x, again, minus 3x, that's the 3, plus 3 equals 0. And again, these do combine to a minus 5x. And then we factor by grouping. So we get 2x, becomes x minus 1. We're going to factor a -3 out of this one, and we're going to get an x minus 1. The reason we factor a -3 out is because we always want the insides to be the same. And now we factor out an x minus 1 from both of them. So we get x minus 1 times 2x minus 3 equals 0. All right. And that's how it factors. So again, if you want to keep on working with these x's, you can. But I find that what makes the most sense to me is to write the factored form with trig functions over here. The reason we had to multiply it to 6, Brock, is because we had a 2 up in front. We're using the AC method. So we have to multiply A times C when we're factoring it. If there was no 2 here, then it would just be the 3. Since there's a 2 here, that's the method of factoring when you have a coefficient in front of the x squared. Does that answer your question? When you get the 2 new numbers, you replace the b with them. Yeah, exactly. When we find this -2 and -3, we split up this b term. Because minus 2x minus 3x is minus 5x. So it still works out. And these are just the choices that we use, so that factoring by grouping is going to work. Good questions. Thank you, guys. All right. So again, if you want to keep on going this way, you can. Actually, yeah, let's keep on going this way, right? We know how to solve this. This is true when x minus 1 equals 0 and when 2x minus 3 equals 0. Quadratic equation will never go wrong, but you can go wrong. There's a lot of simplification in the quadratic equation, but you're right, you can always use it. But so many times I see people use the quadratic equation and just make simple mistakes that a lot of times they don't make when they're factoring, if they are comfortable with factoring, of course. Yeah, it's really easy to make algebra mistakes with the quadratic formula, so I don't recommend it, but you can definitely use it, yeah. So we just add 1 to both sides, you get x equals 1. Over here, add 3 to both sides, you get 2x equals 3. Divide by 2, you get x equals 3 halves. And don't get too excited. You might say, that was great. That wasn't that bad. We're done. But we are not done. Right? Because we're solving for theta. So you told me what x is, and that's all well and good. Notice we were doing it all off on the side. We need to know what theta is. So now it's time to unsubstitute. I don't think that's a word. I'm pretty sure I made that up. So x is the sine of theta. So we replaced the sine of theta with x. Well, now we got to replace it back, right? X is equal to the sine of theta. So we're replacing x with the sine of theta. We have the sine of theta equals 1, and the sine of theta equals 3 halves. We just took these two equations and replaced the x. So we're going to solve this one first, because this one is super easy to solve or super hard to solve, depending on your point of view. When is the sine of theta equal to 3 halves? Hopefully you remember what your graph of sine of theta looks like. You get that if you graph sine of theta back to chapter 8, right? You get that it always oscillates between 1 and -1 forever. Sine of theta never got that big. Okay. Or, again, if you don't remember, you could use your calculator, right? What is the inverse sine of 3 halves? You type inverse sine of 3 halves, it's going to say, domain error. It's going to give you some kind of really grumpy message, all right? This equation is impossible. That can never happen. There's no solution to this one. So we only have to solve this. That's kind of nice. All right. So let's only look at this. This will have a solution because, again, sine oscillates between 1 and -1. But remember, this is like a fringe case. There's no triangle that's going to do this, but we can think of sine of theta as the y-coordinate on the unit circle. So when on the unit circle is the y-coordinate equal to 1? Yeah, exactly, 90 degrees or pi over 2. Good. It's right there. 90 degrees, a quarter of the circle, or pi over 2. And that's the only place that happens. So we just get that, well, theta is pi over 2. We take our solutions to this equation and the solutions to this equation, we put them together. Theta is pi over 2 or 90 degrees. Again, I will take degrees as an answer. And there were no solutions to this one. So this is actually our only solution to this equation. And again, one of the advantages to solving equations in math is that you can check your answer. You can't know that you found all the correct answers, right? Maybe there was another answer that we missed. But we can definitely make sure that this is an answer. So if you have extra time, right, just type it into your calculator. 2 times the sine of pi over 2 squared minus 5 times the sine of pi over 2 plus 3, is that equal to 0? You just type that into your calculator. Make sure it's in radians. 2 times the sine of pi divided by 2 squared minus 5 times the sine of pi over 2 plus 3. That equals 0. So we solved it, checked our answer. It does. All right, and that took me what? 10 seconds to check? It's a good idea. All right. That was part A. Any questions on this before we go into part B? Part B is going to be a doozy. We're going to use a new page for part B because we're going to need a little space. Alrighty then. Let's do 4B. What we have is the cosine squared of theta plus 3 times the cosine of theta minus 1 equals 0. And again, this is a quadratic equation. Remember, the first thing we always said to do for these in this section is we need to solve for the trig function. So we need to solve for the cosine of theta, but it's a quadratic equation, so we'll have to try factoring, complete the square, quadratic formula. These are all valid methods here. I don't like completing the square here just because I don't really like dealing with fractions for completing the square, but you can if you want to. All right, so we're going to, again, use a substitution where x is the cosine of theta. Well, then this becomes x squared plus 3x minus 1. And we'll try to factor it. We need something that multiplies to -1 that adds to 3. I don't think so. So we're going to use a quadratic formula. And like what was mentioned earlier, quadratic formula works for any quadratic. It will always work for a quadratic formula. But you have to be careful. Don't rush yourself. You have to be careful and make sure that you're remembering the formula correctly, as well as make sure that you're simplifying correctly. So what we get is we get that x equals -b plus or minus square root of b squared minus 4ac all over 2a. All right. And then we just keep solving, right? So a is the coefficient of x squared, which is 1. B is the coefficient of x, which is 3. And c is the constant, which is -1. And remember, coefficients, you need to look at the sign before it. So, right, we know this is +1 because there's no negative. We know this is +3 because it's +3. If this were -3x, and b would be -3. So, what we've got over here, we just plug it in. -b is -3. Plus or minus the square root of b squared. 3 squared is 9. Minus 4 times a, which is 1. Times c, which is -1. Be very careful with these negatives inside the square root in the discriminant, as we say. Negative times a negative is going to become a positive. And 2 times a is again 1. And we just simplify this, right? So what do we get? We get -3 plus or minus. This becomes square root of 9 plus 4 is 13. Oh boy. Divided by 2. So this is an interesting one. We're going to need to approximate our answer because we're not going to be able to find exact answers for this. Do we get to? There will be no complex solutions in this section. I can say that with almost certainty. If there is a complex solution, just don't do it. Just say no real solution. We're talking about complex numbers with trig in chapter 10. It's not as bad as it sounds, but we're not going to talk about complex numbers with trig until then. All right. So you shouldn't see any in this section. I haven't done like all the problems or anything, but I'm almost positive it's not going to show up. So we're going to need to approximate. Again, this is x. We don't really care about x, right? We care about theta. X is the same as cosine of theta. So we could just replace the x with cosine of theta if we wanted. And just like before, we have two solutions to this equation, right? So we're going to split, just like in the previous example, into two equations. One of these is going to be when is cosine of theta equal to -3 minus the square root of 13 over 2. And the other equation is going to be cosine of theta equals -3 plus the square root of 13 over 2. Remember, plus or minus just means one of your answers is a plus and one of your answers is a minus. And we just solve each of these individually. And we're going to approximate. We're going to have to approximate anyway, so we're just going to approximate now. Let's see what that left-hand side is equal to. -3 minus the square root of 13 divided by 2. That's -3.3028. And now this should make you very happy or very sad, depending on your point of view. It makes me very happy, as I, don't like to do more work than I have to. Why is this notable? This thing right here. Why is this -3.3028 notable? While you're answering that, I will write down this one on the right-hand side as well. It's going to be with a plus square root of 13. Which is going to be 0.3028. Domain error not defined, something like that. Yep. The cosine, so the range of cosine. So the range of inverse cosine is 0 to pi, Alex, but it's not exactly the same thing here. It's the fact that the range of cosine is -1 to 1. So again, domain error, there's no solution to this. So we only have to solve this other equation to get there. All right. So what we have over here, we need to solve this equation. This is just like example 3 now. Again, we're going to need to approximate. Okay, so we need to take the inverse cosine of 0.3028, and let's see what that equals. That's going to be approximately 1.2632 radians. And again, if you want to think about what is this as degrees, you can convert it to degrees. It's a good idea to have an idea in your head. This is about 72 degrees. Which is a little warmer than it is outside right now. I woke up this morning, it was 9 degrees. I did not know it was going to get so cold right now. I think I have some snow falling as well. It's interesting. I love the weather here. The weather in Wyoming is bananas. Just always changes. It was kind of funny though, because my house got cold. I turned off the heater when it was warm. I was like, why is the house so cold? I checked my phone. Oh, that'll do it. All right, let's finish this problem. So that's going to be our reference angle, right? About 72 degrees is our reference angle. We need to find what quadrants. What quadrant is cosine positive? Just like before, first and fourth quadrant. The first quadrant, if you will. So, roughly 72 degrees in the first quadrant and 72 degrees in the fourth quadrant. These are going to be our two answers. And remember, we were asked specifically about the answers in the interval 0 to 2 pi. So one of them will be that 72 degrees, that 1.2632 radians. And the other one will be this big angle over here. And again, there's a bunch of different ways of finding the big angle. Here, we can just start with the small angle, right? Theta is about 1.2632. We already found that. The angle in the fourth quadrant you can find in a couple different ways. But we know the reference angle, right? The reference angle is that 1.2632, about 72 degrees. So you could go all the way around 2 pi radians and then just go back the reference angle. And yeah, in degrees it would be about 288, I think. So 2 pi minus 1.2632 is going to be that second one. And that's going to be approximately equal to, I have no idea, 2 pi minus 1.2632, approximately equal to 5.01, crap. It actually rounds to 0200. So our second one is 5.0200. And these are our two answers. And remember, even though there are zeros here, we're rounding to 4 decimals. So you need to include the zeros to indicate your precision. All right. Also, one more comment about the degrees. This problem is asking for 4 decimal places, but notice I'm not using 4 decimal places in the degrees. That's because I'm not using degrees as my answer. If you have degrees as your answer, you need more decimal places than this. The only reason I'm having degrees here is so that as I'm solving the problem, I have a visual indicator of what's going on. Because I don't know. I mean, I could figure it out if I spent some time, but I don't just immediately go, yes, my favorite angle, 1.2632 radians, that's right here. But I do know that 72 degrees is about right here. So the degrees can be a good visual aid. Okay. Will a domain error always appear? No. I think it will appear very frequently in the section, but no, it will not always appear in one of these problems. That is a good question, though. But yeah, it's just factoring problems. Sometimes a factoring problem will have one of the answers being bigger, or same with the quadratic formula. If B didn't have a domain error, would we have 4 answers? Yep, probably. Almost certainly. Yeah, that's very possible. All right, I'm going to try to do 2 more problems before we finish out today. And we do need to finish the section today, so I'm not going to finish all the problems remaining, but I'm going to set them up, okay? Just so that you can see them, because there's a lot of tricky things that can happen in this section. All right, so let's go on to part C. Again, if there are more questions, feel free to add them and I'll go back. Part C is sine squared of theta equals 2 cosine of theta plus 2. Now, this one might look the same as the previous two. You say, oh, we got a squared. This is a quadratic equation. But if it's a quadratic equation, how do we substitute? Right? Do we let x be sine of theta or the cosine of theta? It's a problem that these are not the same. And there's a couple of ways to deal with that problem. One of the ways is with, wait for it, trig identities. We can use trig identities right here to turn this into a cosine. Yeah, and which identity you want to use is up to you. Okay? Some of them are better than others. Actually, I think this one really only has one identity that makes a lot of sense. We can look for an identity that turns a cosine into a sine, or an identity that turns a sine squared into a cosine squared. One of those two. So think about which identity you want to use right here. And while you're thinking about it, send me the extra credit question for today. For extra credit today is, give me the name of a kind of furniture for today. A kind of furniture in Discord for your attendance points for today. And then let me know which identity we're going to use here. So pull up the identity sheet and you just scan it. We have a sine squared that we want to turn into a cosine squared. Pythagorean identity will work. Power reduction formula, we don't want that because then we have a cosine of 2x, or a cosine of 2 theta. And we can't work with that either. There's also a sine squared right here, but again, that's sort of the same problem. So this is the Pythagorean identity is really what we're going to want to use. All right, so sine squared of theta plus cosine squared of theta is 1, but alternatively, sine squared of theta is equal to 1 minus cosine squared of theta. Okay, so you just replace that. 1 minus cosine squared of theta equals 2 cosine of theta plus 2. And what you'll do is you'll put this in standard form and solve, just like we did before. All right. Right. Standard form is ax squared plus bx plus c equals 0. We don't have time to go through the trig again, but we've done the trig a few times and it'll be the same. Put it in this form and you'll either factor or use a quadratic formula. Okay. Similarly, part D. Cosine of x times the cosine of 2x. This one's a cute little problem, but it's kind of tricky, which is why I want to show it and not just skip it. Equals root 3 over 2. So it's the same idea. We can't use a substitution because we have a cosine, we have a sine, and we have different insides too, x and 2x. So we need to use an identity. And this one, we're going to use an identity backwards. So we're not going to look for a double angle identity, because if we use a double angle identity, we just get more of a mess, and it's going to be really hard to make anything happen. Not impossible, but really hard to use a double angle identity. So we're going to look at it backwards. We need to find an identity where the output is cosine of something times cosine of something else, plus sine of the first thing times sine of the second. Right? Cosine the first, cosine the second, plus sine the first, sine the second. That hopefully will remind you, or you can scour your sheet, of sum and difference formula. Cosine of the first, cosine of the second, plus sine first, sine of the second is angle difference formula. Actually, Brock, I didn't think about product to sum. I don't think product to sum would... wait. It's very close, actually. And you might be able to use... I'm pretty sure you could do something with product to sum here. I think it'll be harder, but I think it would work. So yeah, since we have a plus here in this formula, that means it has to be a minus over here. So this is cosine of u minus v. All right, this is u, this is v, and this whole thing is cosine of u minus v. So what we have here is this whole thing is cosine of u minus v, but u is just x, and v is just 2x. So we could just simplify this left-hand side and solve it, and it would be not too bad from there. Okay? So the last problem that I do want to solve, and it will be a little late today, but I really want to solve it in depth because it's a little weird, is this problem, part E. The cosine of 2x equals 1/2. And you might say, well, this isn't bad. It's already solved for the trig function. But the 2x really is annoying. Okay? So there's two ways of doing this. One way is to say, I don't like the 2x, let's get rid of it. Get rid of 2x with an identity. Or the second way would be to use a substitution. say like theta equals 2x and solve it that way. I think the second way is a lot harder and a little bit more confusing. So let's just solve it the first way. Actually, they're both hard and confusing. So let's just talk about how you would approach this. Cosine of 2x. You have a choice of any of these. Well, only one of the, this first one will not be helpful. You will not be able to solve it with the first one. So you would have to use these other two to solve it. But I'm going to show you how to solve this with the substitution. All right. So you just say, okay, theta is equal to 2x. But here's the tricky part. Right? Because sure, that's nice. If theta is 2x, we just get cosine of theta equals 1/2, and we can solve that, no big deal. But right, if x is between 0 and 2 pi, what is 2x between? Right? Because theta is 2x. If we're solving something in terms of theta, we need to know the domain. X is going to be between 0 and 2 pi. So 2x, just multiply everything by 2, is going to be between 0 and 4 pi. And remember, 2x is theta. So when we're solving this, we're solving for all the theta in 0 to 4 pi. Okay, so not just the normal angles, 1, 2, 3, 4, also plus 2 pi only once for all of those to get all the values of theta. All right. So let's go through this. I'm going to go through it a little quick. I apologize because we don't have a lot of time. You can always ask more questions after. So when is cosine equal to 1/2? Well, you can use your triangles to say that it's going to be when theta is pi over 3. And we know it's going to happen in the first and the fourth quadrant because that's when cosine's positive. So we have this situation, pi over 3, 60 degrees in the first and fourth quadrant. So that's going to give you pi over 3 is going to be this answer in the first quadrant. Negative pi over 3 is going to be this other one. But negative pi over 3 is not in the domain. So we're going to add a 2 pi to get the positive coterminal angle for pi over 3. And when you add this, you multiply it by 3 over 3, you're going to get 6 pi over 3. The other one's going to be 5 pi over 3. And these are the only solutions for theta in the interval 0 to 2 pi. But remember, x is between 0 and 2 pi, but theta is between 0 and 4 pi. So we actually need the two coterminal angles for each of these. Because there's going to be two more solutions. So if we add 2 pi to this, we're going to get 7 pi over 3. If we add 2 pi to this, that's 6 pi over 3. We're going to get 11 pi over 3. So we actually have 4 answers here because theta is between 0 and 4 pi, because theta is just 2x. We did a substitution that changed our domain. And again, just like with the quadratics, we don't care about theta in our answer. We care about x. Theta is 2x. So our answers are when 2x is equal to pi over 3, 5 pi over 3, 7 pi over 3, and 11 pi over 3. And this is easy to solve. Just divide everything by 2 to solve for x. So x is going to be equal to pi over 6, 5 pi over 6, 7 pi over 6. And 11 pi over 6. And I think these are some of the worst ones. These ones and the quadratic formula ones. All right, and that is all the time that we have for today. But if you have questions, I'll stay a little late and answer them. Okay? So this is the end of the lecture, but if you have questions, go ahead and ask them now. And this will be on your quiz on Wednesday. And then we'll start 10.1 on Wednesday as well. All right, it seems there are no questions, so... Oh, there is a question. Yeah, so this one, to solve this one, you just do a little algebra and one small trig sub. Because what this one becomes over here, if I go off to the side, right? Cosine of x minus 2x, well, what is 1x minus 2x? It's negative x. And then we can simplify the left-hand side as well. Answer your question right after Brock. So cosine of negative x, remember, we can use a parity identity on that. Cosine of negative an angle is the cosine of the positive angle because it's an even function. So this really just becomes, when is cosine of x equal to root 3 over 2, because these two things are the same. And you're going to get a reference angle of pi over 6 for this one. If it were sine or tangent, the negative would come out in front, but cosine, it just goes away. So that's what this one would have become. So to find the other coterminal angles right here, remember coterminal just means the same terminal side. So one angle with the terminal side right here is just pi over 3. Another one, though, is going all the way around 2 pi and then going pi over 3 again. Or we could add another 2 pi, or another 2 pi, or another 2 pi. So we just added 2 pi to our first two angles. And just like before, if we're adding 2 pi to an angle like pi over 3, you just multiply it by 3 over 3, and you're going to get 6 pi over 3. So this plus 6 pi over 3 is 7 pi over 3. This plus 6 pi over 3 is 11 pi over 3. Good. Thank you for the questions. Any other questions? Yeah, what's up? Yeah, you're welcome, Alex. So if you get a less than an 80% on this Wednesday's quiz, then you will have to submit the next week's assignment, which will be 10.1. This week is 9.5 homework. Next week will be 10.1 homework. We'll also start 10.2 next week, but we'll not finish it in time for it to be due next week, Wednesday. With D, you would solve root 3 over 2. I think you got your number switched, but yeah, root 3 over 2, just like the previous ones. Yeah, and you'd use your special triangles. So pi over 6, pi over 3, 1, 2, root 3. Cosine is adjacent over hypotenuse, so you get pi over 6 with this one. Yeah, good. Any other questions before I release you? Actually, you are already released. Not holding anyone here with chains. Ah, we're getting a little bit of snow. How cute. Yeah, you're welcome. All right. I'll talk to all of you on Wednesday. See ya.